Now, what is happening here? Basically the development in ultra fast technology or metrology is as follows. We can compare this with the other important aspect of technology that we know, which is electronics. We know that electronics is driven by Moore's law, which essentially says that the number of transistors on a chip, on a given area of the chip, doubles roughly every 18 months. But this is, why is this important? It is important because things scale, costs come down, but also other properties get enhanced. The speed of electronics, as you can see on this semi-log plot, is falling down pretty fast. It is super exponential, okay. But although it seems to be plateauing over here sometime, I do not understand why we have these little red lines, but so be it. But if we look at photonics or optics, it has beaten electronics in the somewhere between the 60s and 70s in terms of the time resolution or speeds. So, this time resolution in electronics converts to processor speed, which is on the gigahertz range as we speak. So, if we had similarly exploited the speed of or the temporal advances in reducing the temporal resolution in optics of photonics, such processors equivalently today may have certainly cracked the even the terahertz limit or whatever. It would not have remained in gigahertz, it would have gone into terahertz and so on. So, we would have had 1000 times faster computing, but the fact remains that we still cannot do that type of computing with light alone. But as we speak, indeed this whole idea is making a comeback, if you wish, where optical chips are also being made, and there are companies as of 2024 which are we can say startups which are essentially doing optical computing, linear, this is no quantum, nothing, just photonic approaches to computing. The challenges there remain the amount of error that creeps into this process, and strategies like nested Mach-Zehnder interferometers and things like that are applied. Of course, on chips which are integrated optics, those chips again have not scaled down in terms of the number of elements as Moore's law dictates here, but still that seems to be a future direction in micro, should we call it electronics or photonics, but that is there. So, but then what one can see on this plot is that there is a cusp here around 2000s when once again optics more or less suffered the same fate as electronics is today, where the shortest time resolutions we can handle started to saturate. But something happened here in early 2000s which led to a phase change, if you wish, or a substantial change, and mankind running away with another new trend in this plot. Therefore, it is no surprise that pioneers who are responsible for this cusp, this inflection point, if you wish, were awarded a Nobel Prize, and I do not have really an updated chart here, but say somewhere here, right. So, will this go on from Atto to Zepto and whatever? Yes, maybe it will, that is the optimist talking, but for a student of science, physics or engineering, the question that we may want to ask is, what happened here that there is this inflection point? What was the change, such a drastic change which happened, all right. So, in terms of economics, if we saw this, it could be like a market crash. So, we immediately ask what happened. Oh, maybe there was a pandemic, if the variables we were plotting was not time, but something else on the vertical axis, such as GDP or some such thing, right. There must have been an abrupt event that took place. So, in the physics universe, there must have been some sort of discontinuity that occurred, something changed, and that of course we know is the reason why the pioneers of this science won the Nobel Prize this year. With that point made, ultra fast phenomena, which today we are discussing in terms of things with lasers, all right, are ramping up or literally galloping all the way from the first Nobel Prize given for this science in the year 1995 to Professor Ahmed Zewail, who carried out this pioneering work at Caltech, the California Institute of Technology, where essentially he studied the galloping or the motion of molecules on sub-picosecond time scales. So, that was the 90s, but look at how quickly the field has advanced. In the 1940s, it was microseconds. Now, it is the time scales that we could handle shrunk down by more than a factor of a million, from micro to pico or sub-pico, right. So, this is rapid advancement, and which is the trend that this plot captured with this super exponential decay in the time resolution and the shortest time events that we can create, measure actually, which is very important, and we can even manipulate. Okay. As time progressed, by the early 2010s, we got into the atto world, that is sub femtosecond world. So, again another jump in about this time, a shorter, you can say, time span. We reduce this by another million, order of magnitude, that is not order of magnitude, million fold reduction, right, in the duration of the time events that we can create, measure, manipulate and apply. Okay. So, that is the whole point, but all of this begs a question, pushes us to ask a question: what is it? The key question is how. How do you even know, if one were to be a pioneer, or you were to be a practitioner or a researcher or a student, that you indeed have these shortest, as we have been proudly claiming, events in your hand? How do we know that we have these events in our hand? We are claiming it to be the shortest. How do we know? Because we said seeing is believing in the case of horses galloping. Right. But as with any phenomenon, of course, seeing pertains to the human eye, we still want to have a certain amount of belief even in science, although we often associate science with sometimes the antithesis of belief or rationality and so on. But even at a philosophical level, the existence of something we need to unquestionably, undeniably establish. As far as science goes, this believing should now become synonymous to measuring. After all, seeing or vision is measurement with the human eye or equivalent. Right. So, measuring is believing. In other words, as Professor Wayne Knox very elegantly put it, if you haven't measured it, you haven't made it, as simple as that. The counter thesis to this is the emperor's new clothes, if one may say so, if you know what I mean, the parable of the emperor and his new clothes, right. So, the whole point therefore is to measure things that we claim to have made, isn't it? Otherwise, it is a hoax or a heist or whatever such we could call it. If it is money, it is money heist. If it is hoax, it is, I don't know, a magic, yeah. It is just a magic show at the end of the day, which ends the moment the magician disappears away from the stage. And if I may refer to the Hollywood movie The Prestige comes to mind, for example, right. So, it is only that, it is only of entertainment value. But if it were one were to take this seriously, and you know, a favorite quote that I like recalling from Professor Richard Feynman is, what I cannot create, I cannot understand. But that is of course on sort of theoretical framework of footing, but for in pragmatic, practical real world terms. If you haven't made it, you haven't measured it. So let's measure. That's the whole idea. How do we measure? Before we say ask how do we measure, what are we measuring? We are measuring events and time. Okay, whatever may be the event. Here the event is a light pulse. But a very sort of basic common sensey notion that goes with measuring things in time, such as the clock that is ticking behind us or in front of us or wherever, is the fact that to measure an event in time, we essentially need a shorter one. That is to say, in the language of a classic good old clock, okay, that was basically a bullet tearing through a card. If you heard that sound, that's basically a short event, right. Essentially, a clock, the way in which it works is kind of like this. We do not see this happening on clocks, but the idea here that is conveyed is that the slower hand of the clock that is rotating does not keep the time by itself. The time for its motion is kept by the faster hand that is rotating even faster. So, the minutes hand of a clock, which is, let us say, the faster hand here, its time is kept by the seconds hand. Or if this slow one was to be the hour hand, the minute hand kept its time. That is why we say that an hour has 60 minutes and that a minute has 60 seconds and a second has not 60 but 1000 milliseconds, right. So, therefore, in a clock that is ticking every second, there is some other timekeeper operating at shorter than a second or on millisecond time scale. So, there is a timekeeper underneath all this. So, we can extrapolate this and ask who is the ultimate timekeeper, right. I mean, I am not asking this question in any philosophical or religious terms, practically speaking. So, there must be somebody who is keeping time. If all our mobile phones and our digital electronics is synced up, so that every time we pick up a mobile phone, all of us invariably read the same time, which we call the internet time. Okay, so internet is not a company run by a philanthropist who is keeping time for us. No, there is somewhere a clock that is sitting and measuring time, which are primary sources of tempo metrology in time, which in India is the National Physical Lab in New Delhi, which there is an analog say in France, it has to be somewhere in Paris, then in Germany, not in Berlin as far as I know, it is in Braunschweig in PTB, and one of the gold standards certainly is in the US, again it is in Colorado, in NIST in Boulder, Colorado, right. So, they are all standards institutions. NIST is the National Institutes of Standards, right. So, NPL in India is National Physical Laboratory. Of course, we set our Windows PCs to Windows time. So, Microsoft is borrowing information from these institutions. In fact, we must be paying them some money to do that, which helps us to measure time carefully enough. For example, and this is done to extraordinary precision, we may have discussed this in an earlier lecture, right. The definition of a second runs to better than a nanosecond, that is better than 10 digits, which ultimately also becomes important for us to use Google Maps, that is GPS systems, because GPS systems work based on triangulation, and this triangulation necessarily requires a certain basic minimum level of precision that we have in timekeeping, right, which is also why there are efforts to send atomic clocks even into space and so on and so forth. It is a beautiful field in itself. One can learn an entire course, if not do a PhD, or as some practitioners do, spend an entire lifetime on metrology, researching it, furthering it, and therefore literally advancing human civilization, and still not be done with it. So, it is going to be a continuing task. Now, What is the problem with temporal measurements of measuring the shortest events? This is the problem. What can you make of this clock? If there were to be such a clock where the dial itself is rotating and there are hands, this would at best be of comic value in a display or entertain ourselves with something crazy like this, but nothing more, right? Why? What is the problem with this clock? It has a dial, it has two hands, the minute and the seconds hand. So, it should be just as good as anything we see on on our watches in the hand or mobile phones or wherever else, or a clock hanging on the wall. What is the problem with this? What is the problem, by the way? Too fast. Okay.
We are not in a frame where the dial is stationary.
So, what is the dial after all? Do we actually need all the 12 numbers to be put on a dial? Actually, there are artistic analog watches where maybe there is almost nothing, but it pushes us to use our mind's eye to at least put one mark somewhere to mark the 12 o'clock or the 0, right. The problem with this dial is, therefore, in other words, there is no reference. If a gram of gold costs approximately 6,000 Indian rupees as of today, I may be off by something the exact number, but that is the approximate cost, right. So, then what is, there is a problem with that. You need a very accurate definition of the gram or the kilogram, and that to be maintained across various transaction points to be able to do some successful business and so on. So, therefore, even in commerce, this plays a huge role. In fact, the role that these play in commerce is probably greater than in science, which is also why a whole lot of investment goes into it. The whole point is there is no reference point in a random clock like this. This is also the problem for us now. If we have claimed, you, me, anybody claims that they have made the shortest pulses or events, apart from the definition of shortest itself, which we will see how we can handle, the question is, how do we know we do not have an event shorter than this to measure the duration of these events in time? Because shortest means is the same as nothing shorter. So, we have put ourselves into a corner. We have just gotten cornered by saying that we want to measure the shortest pulses, right. We need to wriggle out of this somehow, right. So, any ideas how we should, what route or path we should take for this? I probably already gave you a part of the answer, but that is not the whole answer, or maybe you have better ideas. How do we wriggle out of this problem of not having a reference? Any referential thoughts from the class? So, Amna says self-referencing.
So maybe like a delayed version of the same question.
Self-referencing. I am the richest man on the planet. Self-referencing, which is my wish. Let us just say that is an example of, I mean, financially, monetarily richest, not philosophically. Can say I am the happiest today, it is a self-reference. That is the problem with self-references. Or okay, Amna says delayed references. Okay, you will have to qualify that for us at some point. Oh, I am not a very punctual person, so I am a delayed reference of myself. I wish I were to be at some point on time, but luckily I didn't miss my flight yesterday, so but my flight was delayed by 10 minutes, so that's delayed reference. But a delayed reference, yes, so please keep these words in mind. I am sure my friend here is speaking this out of some wisdom. So as she says, self-referencing and delayed referencing. Delay and self-referencing are kind of maybe our only choices, but let's develop the idea further, right. So first of all, we need to search for a reference, but this is a problem only for us people, or is this really a problem? What if we somehow produce the shortest acoustic pulses? By acoustic pulses, I mean the pulses with the frequency content in the human auditory range. Which I think extends up to 100 kilohertz, right? This is of the order of 1 to 100 kilohertz. These are ultra fast acoustic pulses. Can we measure them? Of course we measure them all the time, right? So ultra fast detection in acoustics is not a problem at all. But what was the solution to the challenge there? We had another, say, a complementary or enabling technology which came to our rescue, and that technology was essentially faster. So we were able to, instead of self reference in this case, we were able to cross reference. The reference lay elsewhere in another domain. We simply borrowed it and solved the problem here, because electronics is much faster than acoustics in this case. We have defined the frequency range, even if it is to be ultrasonic or hypersonic. You can add 3 more zeros to it, you are still at megahertz and whatever, but every phone and stuff has gigahertz electronics. So this is seldom going to be a problem for acoustics, one can say. Of course, there will still be challenges and the such in terms of engineering the device and technology, but at least in an in principle sense, we don't need to be worried that we have hit a dead end or we have hit a roadblock, such as Moore's law is hitting today in the semiconductor technology, the roadmap of the semiconductor technology. So therefore, a cross reference, we should maybe search for cross references. Actually, even in the optical side, right, in optical metrology too, if we look at frequency metrology, what actually saves the day for us is a cross reference, because we cross reference the metrology of optical frequencies, optical and microwave frequencies, to nature's gift, which is atomic transitions. If you wish, these two are somewhat different in the sense that optical frequencies talk about light, whereas atomic references talk about matter, and we can say the universe is either light or matter. It can't get more complementary than that. It is as complementary as yin and yang or whatever notion that we can have. They are two very different elements, although one produces light with matter from matter in some sense, and light modifies matter and so on, as we have discussed, but then they are very complementary. We reference or log frequencies to atomic transitions because they are the purest of frequency keepers available to us. So the cesium clock that we talk about is referenced to not any but particular transitions between hyperfine levels in the cesium atom, an alkali atom, right. So there we used, again we are cross referencing. Really, if you were to be doing your PhD in the 70s and your advisor set up this problem for you to measure the shortest time pulses, the wisest decision you could have taken is to simply walk away from that project. Because look at this, the same thing in the frequency domain had some hope perhaps to finding a solution by cross referencing acoustics, yes, but only in the optics and time domain we have a problem where measuring these shortest references is probably you know let us just say fail before start scenario for someone taking up a research project. Too hard, too challenging maybe, but of course that is also a triumph of human spirit. People figured this out, and we can measure the, or rather than say we can measure, I think we should say we can get a measure of the shortest photonic events created by man, or mankind I should say, I should not say mankind, humankind, in the time domain. That is the whole challenge. So, we, all this rambling apart, the idea is to here to set up the problem and state it in very clear terms. Ultimately, as we will see, this also pertains to frequency domain measurements or wavelength domain measurements and so on. But then maybe before we proceed, and we should not forget that the whole limitation comes about because photonic, or we can say photo or opto electronic detectors are far too slow to help being the solution for this, whereas acoustic detectors can be really fast and we could measure amplitudes in this case, whereas as we discussed earlier in the course, we here end up measuring signals which maybe I should refrain from writing this integral. We measure a signal which is essentially integrated over many cycles of the oscillation of an electromagnetic wave.